Okay, this video is to review the essential skill logarithms. So this page has a lot of important properties that you should be writing down. So at the top you can see the rewrite formula. So to go from a logarithm equation to an exponential equation, or to go from an exponential equation back to a logarithm equation. Both are equally important. Notice that the little subscript of your logarithm is a. That's called the base. We don't call it the subscript. It's log base a. And over here in my exponent equation, the base is a. Also notice that in the logarithm form, the a and the b are on the same side of the equation, but when you rewrite it, they will no longer be on the same side of the equation. And the exponent is what a logarithm is equal to, so when you rewrite it, the exponent is up in the air. The laws of logs: when you have logs with matching bases, so it is always assumed the bases need to match. If you are doing log m plus log n, you can rewrite that as just log of the m value times the n value. So for logarithms, add means multiply. If you have log of m minus log of n, you can rewrite that as log of m over n, so the log of the division, so subtraction means divide. And if you have a times log of m, you can float that up and it becomes the exponent on the m itself over here, and it becomes log of m to the a power. All of these log properties work both directions. Often we are condensing, but there might be a time where you are asked to expand as well, and you'll need to go backwards. Then there's some quick properties down at the bottom. If you're taking log base a of a, the answer is just 1, because there's a little imaginary 1 in the exponent on that a. Kind of same idea, if you're taking log base a of a to the b power, the answer is the exponent, because when you take the log of something, you are looking for the exponent. When you do log base a of 1, the answer is always 0, and that's because anything to the 0 power always equals 1. And if you have a and you're raising it to the log base a of b, the answer is just that b value. Over here, these are some things we will never do. We will never take the log of a negative, that has no solution, and we will never take log of 0, that also has no solution. That is why when we graph logarithms, they have asymptotes. You cannot take logs of 0 or negative numbers. So let's put these properties to use. First, we start with evaluating. So these are just cute little 1-point questions. Evaluate log base 2 of 16. It is possible to do this in your head, depending on how far along into the chapter you are. But if you don't want to do it in your head, when it says evaluate, it wants to know, what does this equal? It equals x. Well, this is a good time to change from a log equation to an exponent equation. So I didn't do that over here, but oftentimes we circle the subscript, the base, and draw an arrow over to the c, and that's how we get a to the c power, and then it equals what's left, b. So if we do that here, circle the 2 to the x power, 2 to what power equals 16. Oftentimes when people see log base 2 of 16, they think to themselves, 2 to what power makes 16? This is an exponent you're going to have to memorize. 2 times itself, how many times? 2 times itself, 4 times. 2 times 2 is 4, times 2 again is 8, times 2 again is 16. The answer is 4. 1 point just for getting it right, so you do not need to show any work if you can do this in your head. So when you see number 2, what are people thinking to themselves? They're thinking 3 to what power equals 27? Well, 3 cubed is 27, so the answer is 3. You don't even need x equals, just 3 is good enough. Number 3, we're thinking 5 to what power equals 1 over 25. In order to get fractions as an answer, you need negative exponents. So in this case, x would have to equal negative, and then 5 squared is 25, so negative 2. The negative gives you a fraction, 5 squared is 25. See if you can do the bottom ones. Well, I guess we haven't done one like number 4 yet. Let me talk you through number 4. So the difference is on number 4, the base is bigger, right? I'm circling a bigger number. 36 to what power equals 6? Well, one thing, hopefully you're learning and memorizing your exponents. One thing you might know is that 6 squared equals 36. So if the x was on the 6, that would be an easier problem. But since the x is on the 36, we want to square root that, And in order to square root, you use a fraction, 1/2. When the base is bigger, you use a fraction. 1/2 because I want a square root. Something to the 1/2 power is the square root of that something, and that's how we get 6. Okay, try 5 and 6 on your own if you haven't yet. Always pause the video and try these on your own if you've already learned it. 2 to what power equals 1/8? 1/8 means negative, and 2 cubed is 8. 125 to what power? So a bigger base equals 5. Well, the cube root of 125 would give me 5. So I want to cube root it. That means 1/3 power. A 1/3 power is a cube root. Okay, let's keep going. Next, we learned how to condense. So we're going to use those laws of logs from my first page, and we're going to condense these down to a single logarithm. When you condense, you still have a log in front of it. Do not delete the logarithm in the front. We are condensing it down. So when we see plus for logarithms, we know that means multiply. And when we see divide, how about minus? Sorry, that means divide. So I'm going to have log 2 of, I know I'm going to have a fraction because there is a minus in this, so that means I'm going to be dividing by something. And the plus ones, now I have the hiccups, excuse me. The plus ones get multiplied and put on the top. So log base 2 of 4 plus log base 2 of x is log base 2 of 4x. But then when I minus log base 2 of 7, I divide by 7. Notice the log base 2 in front of it. Still log base 2, but of 4x over 7. Okay, normally we look for coefficients first, but there wasn't a coefficient on that example. But this example has a coefficient. Remember, laws of logs says the coefficient floats up here and becomes an exponent. So that's really log base 5 of 4 squared, which is 16. So you always do coefficients first. They become exponents. We always do exponents first. Now I see a minus sign, so I know I'm going to have a fraction. The positive one over the negative one. 16 over 7. Log base 5 of 16 over 7. Okay, exponents. Look for those coefficients. Do those first. 1/2 becomes a 1/2 power. We talked about this on the other side. A 1/2 power means square root of 49. Well, that's just 7. So this is really log 3 of 7 minus no coefficient, log 3 of 2. None of these have coefficients. I see some minuses, so I know I am going to have a fraction. I'm going to write my answer over here. Log 3 of a fraction. The positive ones will end up on top together, multiplied together on top. The minus, the negative ones, will end up on the bottom, multiplied together. 7 times 5 is 35. 2 times 2 is 4. I can't divide that, so that's my answer. Log base 3 of 35 over 4. See if you can do the last one. Start with coefficients. I see subtraction. I know I'm going to have a fraction. Only x is positive. That's the only thing on the top. And then the y cubed and z squared are both negative. They get multiplied together on the bottom. Y cubed, z squared. Log of x over y cubed, z squared. Okay, moving on. Solving log equations. You will notice as we go through these, there are only 2 types of log equations that we solve. The first type is like number 1. If you look at question number 1, notice that every single term says log. 3 log 2 plus log 4 equals log x. Every single term has a log attached to it. The first step is to condense. The first step is always to condense when you see logarithms in a problem. So when I see a 3 in front, remember that becomes an exponent. So I'll do that step first. 2 cubed, remember it's an exponent, becomes 8. Then I am condensing. For logarithms, plus means multiply. So this is log of 8 times 4 is 32. Notice how every single term still has a logarithm on it. When you condense, you still have a logarithm on it. Now I have log 32 equals log x. Well, if log of something equals log of something else, logically the something and the something else must be equal. And in this example, we're done. We found x. Type 1. Every single term has a log attached to it. Condense, and then once you have log equals log, the inside parts must be equal. Okay, type number 2. Notice that the left side has logarithms attached to it, but the right side is just a number. We have a single regular number in our equation. We're still going to start by condensing. So minus log of 2 of means divide. 3 over x equals 4. But because the right-hand side, and it doesn't matter which side, but because one side has a regular number, it's just equal to 4, not log of 4, just 4, we want to change this from an exponent problem, from a log problem to an exponent problem. So circle the base, 2 to the 4th power equals x over 3. 2 to the 4th is 16 equals x over 3. Multiply both sides by 3 to get rid of the fraction. Those ones cross out. X equals 48. So when there's one regular number, we condense the logs together, and then we change it to an exponent problem and finish solving. So number 3, one regular number again. The logs are already condensed. It's just a log equals a number. So rewrite it as an exponent problem. Something cubed equals 125. That's one of those exponents you're supposed to have memorized. X equals 5, because 5 times 5 times 5 is 125. Try number 4. We have a single log equals a regular number. Rewrite it as an exponent. 3 squared equals x plus 7. 3 squared is 9 minus 7, and x equals 2. Let's see what's on the next page. Number 5, logarithms and regular numbers. I see coefficients. Do the coefficient first. Float it up to make it an exponent. Log 5 still of 3 squared is 9. For logarithms, subtraction means divide. Log 5 in front still. 9 over x equals 2. Now I have a logarithm equals a regular number. Rewrite it as an exponent. 5 squared equals 9 over x. 25 equals 9 over x. Same idea. I don't like fractions. I multiply both sides by x. I'm going to start up here. I get 25x equals, these cross out, so I just get 9. Divide by 25. X equals 9 over 25. Okay, now we have our third type of log problem. And notice it doesn't even have logs in it at all. It's going to when we're done, right? This essential skill we're practicing is logarithms, but it starts with no logarithms at all. And to start it, you need to get the base alone. So this 3 to the power of x minus 1, you need to isolate that. Get that alone. You cannot multiply when there's an exponent on it. So you need to get it alone just as it is. I'm going to have 3 to the x minus 1 equals something before I finish this problem. So start by moving the thing that's furthest away. So add the 4. 2 times 3 to the x minus 1 equals 14. Then divide, right? We can't change the 3, so we divide to get it alone. Then we can't solve this the way it's written because I don't know any way to make 3 equal 7 by multiplying it over and over again. It's going to be some crazy decimal, right? So if you can't solve something as an exponent problem, you rewrite it as a log problem. So I'm going to go back really quick. Remember up here at the top, the rewriting from log to exponent? Now we're going from exponent to log. So remember that the base of our exponent problem becomes the subscript, the base of our logarithm problem. So here we are. The base of our problem is 3. So it's going to be log base 3. That's the base. And then it's of the other number, so of 7. And it always equals the exponent, equals x minus 1. I'm trying to get x alone, so to finish getting x alone, I have to add 1. You can't actually add numbers to logarithms without a calculator, so it's going to look like log base 3 of 7 plus 1. You can't actually add it, so this is what it's going to look like when you're done. So let's try number 7. Get the 7 to the x plus 2 alone. So add 3. I'm not going to show every step. Add 3. And you get 15. Divide by 5. And you get 3. So once you get it alone, change it to a logarithm problem. What's the base? The base is 7. So log base 7 of 3 equals the exponent. Whatever the exponent is, that's what it equals. Finish solving for x, you have to minus the 2. It just goes at the end, and it looks like this. Number 8, it's a logarithm equals a number, so change it to an exponent problem. 3 to the 1/7 equals x. We will not accept that answer on test day. A 1/7 power is a 7 root of 3. This is what we're looking for to get credit. Number 9, get the log alone first. So when you have more than one real number, you need to get them all on the same side. So minus 1. Minus 1, and I get 2. Then change it to an exponent problem. 4 squared equals x minus 2. That's 16 equals x minus 2. Add 2, and x equals 18. Okay, finally, graphing logs. The parent graph is graphed for you. That is the sketch of the parent graph no matter what the base is. In integrated 3, the base does not do enough to change the sketch. We are only sketching. So notice the original has an asymptote at x equals 0 and a locator point at 1, 0. That says 1, 0. So if we do parent graphs, y equals a log, it doesn't matter the base, of x minus h plus k. The asymptote is always going to be at x equals h. Opposite the parentheses, do not forget the x equals. The locator point is always going to be 1 unit to the right of that, so h plus 1, and then comma k. So we are going to sketch number 1. We want to list out all the things, the asymptote, the locator point, and then we're also going to list the transformations. So looking at that equation, opposite of the parentheses, x equals negative 2 is where the asymptote is. A vertical dotted line through x equals negative 2. 1 unit to the right of that, negative 2 plus 1 is negative 1, comma, and the k value is negative 1. Negative 1 is my point. It hugs the asymptote going downwards and super slowly increases to the right. My transformations, the x plus 2 moved it left 2, and the negative 1 at the end moved it down 1. Try number 2. I think I'm going to have to write my stuff down here. Asymptote, locator point, transformations. So x minus 3 in parentheses means x equals positive 3 for my locator point. Oops, sorry, for my asymptote. 1 unit to the right of positive 3 is 4, comma, and my k value is 2. So positive 3 for the asymptote. 1 unit to the right is 4, comma, 2 for the locator point. Hug the asymptote. Slowly increase to the right. The 2 in front of this does stretch it vertically, but it's so small of a stretch that it doesn't change our sketch. The 3 in the parentheses moved it right 3, and the 2 at the end moved it up 2, just like in Parent Graphs Chapter 2. So hopefully this helps you prepare for your logarithm essential skill. Hope you're doing good.